Welcome to the DD1324 online lectures. In this lesson, we will cover pointers and functions. So we'll begin with something a little more advanced than we worked on in the pointer basics tutorials. We'll look today at pointers to pointers. Pointers can point to other pointers as well as to the standard data types. Pointers to pointers can be confusing at first glance, but if you take the time to look at the syntax, then it can usually be broken down into an easily understandable declaration. So for example, we have an example here where we declare an integer x and we assign it the value of 5. Next we declare a pointer to an integer p and we give p the address of the variable x. Next we declare a pointer to an integer q, and we give this the address of the first pointer p. You can continue doing this as many times as you like. Here you have a pointer to a pointer to a pointer to an integer r, and we give it the value of the address of q. Here you can see a diagram of this hypothetical situation that we just created. So first here at address 64 we created an integer x. Next at address 128 we created a pointer p which points to address 64. So p is equal to 64. It's pointing to 64. And if we dereference it once, then it gives us the integer value of 5. The next pointer we declared, a pointer to an int, is q. The value of q is 128. q is pointing to 128. If we dereference it once, we'll get 64, or the value of p. If we dereference it twice, so chain dereferencing, then we'll get 5. So you follow it first to the first pointer and second to the second pointer, and then you can get the value star star q is equal to 5. The same goes for the pointer to a pointer to a pointer. So r has the address 207 as its value. It's pointing to the memory address 207, which contains pointer q. If we dereference r once, then we'll get the value for q, 128. If we dereference it twice, we get the value of 64. And if we dereference it 3 times, so a pointer to a pointer to a pointer to an integer, we'll get finally the integer 5, which is the contents of the address, the memory location of 64. Next, we'll look at pointers used as function arguments. To motivate this, we're going to look at the following example where we'd like to write a simple function to increment a variable by 1. Here in this example, you can see we have a function that we've written called increment, and it increments integer a, so that a is equal to a plus 1. And we have the main function where we declare the integer a, we give it a value of 10, we call increment, and then we print the value of a. In this example, the code uses call by value, and the output is not what the author expected it to be. Here the author expected that we declared a variable a equals 10, we incremented it, and then we printed it, and we expected the output to be 11, but here you can see the output actually returned a 10. To understand why the program didn't behave as we expected, let's take a look at what happens in the computer's memory step by step as it runs the program. When the program is started, the computer reserves some amount of memory for the execution of the program. That memory is typically divided into 4 parts. First, you have the instructions, which contain the actual code for the program. Then you have the static and global variables. Then you have a stack, which is a first in, last out kind of queue for the instructions of the program. And last, you have the heap. We'll cover the heap in a later lecture. The program begins with the call to the main function, which creates a call frame here of main in the stack. The call frame contains the arguments for the function, its local variables, its return address, and the current instruction. Whenever a new function is invoked, this creates a new stack frame which is pushed to the call stack. Here, when we reach this line of code, main calls the function increment, and this creates a new stack call frame for increment. And when this happens, the call frame also contains the local arguments, variables, and instructions for the function increment. When we do call by value, where we've passed it the value for an integer a here, and you can see here we're doing call by value because we've declared that increment takes an integer value coming as the argument for the for the function, this means that the actual argument is copied into the call frame for increment, or into the formal argument. So that means inside of the stack frame, we now have a copy of the local variable a. So here a is equal to 10, and then we say a is equal to a plus 1. So there's a local copy of a inside of the increment stack frame that has a value of 11, and there's also an a inside of main that still has a value of 10. Once increment is finished running, or finished executing, control returns to the main stack frame, and then the increment call frame is pushed off the stack. Then control passes back to the main stack frame, and the local variable a from increment is removed, but the main local variable a remains unchanged. So now we move to the next line of the code where we say we have a printf for the variable a, and we can see then that it creates a printf stack frame added to the call stack, but it's been given a copy of a equals 10, not a equals 11, and this is why we have the unexpected behavior. So, how can we modify our code so that it properly increments the variable by 1? The trick is that previously we had used functions as call by value, meaning that the actual value of the variable was passed to another function. In this case, it was increment. Strictly in C, everything is call by value. However, we can create the illusion of call by reference using pointers. So instead of passing the actual value of a variable, we can pass an alias, or the memory address, to the function as pointers, which the function can then manipulate and the original function can access later. So here you can see we have our main function. We declare the integer a, we give it a value of 10, and then we pass the address of a into the function call for increment. When we declare increment, we declare that it wants to take a pointer p as an argument. And when we want to manipulate it, we use dereferencing so that we say the value at the memory location where p is pointing is equal to the value at the memory location where p is pointing plus 1, and then the function closes. After that, when we try to access the variable a, it's been manipulated within the increment function, so when we print, we get the value 11. Let's look once more at the code now that we've modified it to use call by reference. So we begin with the main function. So when the program starts the main function, this puts the main function on the call stack, and that includes a variable a, which is equal to 10, and it has a memory address location of 128. We then call increment, but when we're calling increment, we give it the address of a, not the value of a. So when we call increment, this makes a call frame for increment added to the stack. And when we run increment, we notice that in the declaration we're expecting a pointer to an integer p, and that pointer to an integer is given the value of the address of a. P is equal to 128. So this is the variable that's sitting in the call frame for increment. Now inside of increment, we execute the following command where we say the value at the memory location for pointed at by p is equal to the value at the memory location pointed at p plus 1. So this manipulates the value at 128 so that it's now 11, and then increment is popped off of the stack and we go to printf, and when we do a printf, the output becomes 11. Using this call by reference is very helpful because it saves us time and memory by avoiding copying large variables from one function to another. An important thing to remember when using functions that have arrays as arguments is that arrays are always passed by reference in function calls. So that means if you have a function that takes an int array as an argument, it implicitly changes that argument to a pointer to an integer using the base address a from the function call. Let's look at this example here. In the main function, first we declare an array of length 5 and give it the values 90210. Here we also create an integer calculating the size of that array, and we calculate the size of a over the size of the first element of the array, and then we print it out, and that gives us a length of the array of 5. Next, we call a function SUMOfArray, which sums the elements of the array. And here we pass the base address into the function call. Now that's important because we have to remember that A here is containing the first address, the first memory location for element A of 0 in the array. So when we define our function call here, the type that we use for the array is an integer type, and then A, and then the open and close square braces, which is equivalent to a pointer to an integer type, which is basically pointing at the base address that we gave here. So this is passed by reference. So within the SUMOfArray function then, here we also calculate a size of the array. But in this time when we calculate the size of the array, A is now a pointer, and calculating that over the size of the first element gives us a size of 2 instead of a size of 5. So here when we do all of our manipulations on A, they're manipulating the values within the memory location pointed to by A using this base address that we were given here. This concludes our lesson on pointers and functions. Thank you for watching.